Here, these resistances have been expressed in terms of conductance. Now, we could write the value R1 in ohms, R2 in ohms, and R3 in ohms. Here, they are given in Siemens with the appropriate metric prefix, and we got to take that into account now when we try to add those up. Okay. So if we're going to calculate the total current and the current flowing in each resistor, remember that typically we can start in two different ways. We can apply Ohm's law to each of the individual resistances, because we will come to the conclusion that if this here is Vt, that V1 is equal to V2 is equal to V3 is equal to Vt at 120 volts. And so once we realize that we have the voltage drop across each of these conductances and the conductance value, then we can apply Ohm's law to each conductance individually. And so let's start by doing that. All right. And so we'll find the current flowing in each resistor first. Okay. So then remember that Ohm's law, written in terms of conductance, says that I1 is equal to V1 times G1. And so 120 volts across V1 multiplied by 500 microsiemens. And so remember that that is 500 times 10 to the negative 6 Siemens. And put that in your calculator, do the calculation, and you got 0.06 amps or 60 milliamps for I1. Now, in a very similar fashion then, I2 is equal to V2 times G2, and we have 120 volts multiplied by this time 2 millisiemens, and so you can write that as 0.002 or as 2 times 10 to the negative 3, whichever you like. And when you multiply it out, you come up with 0.24 amps or 240 milliamps. And so you see then that as the conductance value gets bigger, because 2 millisiemens is much bigger than 500 microsiemens, that the current goes up. Okay, so more conductance means that it's easier to get a current to flow through there. I3 is equal to V3 at 120 volts multiplied by G3 at 0.01 Siemens, and that is equal to 1.2 amps, or well, 1200 milliamps, I guess we could say. And so again now, a bigger conductance, more current. So the biggest conductance gets the biggest current. Okay, so remember Kirchhoff's current law now tells us that if I want to find the total current, IT is equal to the sum of I1 plus I2 plus I3. and that is equal to, let's go with 0.06 amps for 60 milliamps, plus 0.24 amps for 240 milliamps, and I3 at 1.2 amps, and come up with IT is equal to 1.5 amps. Now, if we used Kirchhoff's current law to calculate that, then in order to verify, we got to do some circuit analysis. Well, remember that this is IT, and in order for us to find it, we have to apply Ohm's law to the circuit. And so we can go ahead and say that, and I understand we're out of time now, so if you got another place to be, that's fine. But if you can, give me a couple of minutes just to finish this. And so now GT is equal to the sum G1 plus G2 plus G3. And so remember now that we got to take the metric prefixes into account. So we got a micro, a milli, and no metric prefix over there. So if we write all of these in terms of millisiemens, 500 microsiemens, remember a milli is bigger. So that means to move your decimal 3 places to the right to convert that micro to a milli. And so then 0.5 millisiemens, equivalent to 500 microsiemens, plus 2 millisiemens, plus 0.01 Siemens is, if you move your decimal 3 spots to the right, yes, and so remember I said 3 spots to the right for G1, but it's left. Here 3 spots to the right gives you 10 millisiemens. And so if we add that up, we have GT equals 12.5 millisiemens, which is, of course, 12.5 times 10 to the negative 3 Siemens, or 0.0125 Siemens. Okay, so then let's apply Ohm's law now in terms of conductance to the circuit. And Ohm's law written in terms of conductance, IT equals VT times GT. And we have 120 volts multiplied by 0. Oh, wait, no. 0.0125 Siemens, and if you do that calculation, lo and behold, IT comes out to be 1.5 amps, which is just what I guess we expected.